Here's the 4.2 video. So our main thing we're looking at here is the difference between an observational study and an experiment. So think about the qualities of each, how they're similar and how they're different. Be sure to think about what type of randomization is included and how can we apply results, what is required to apply our results to the population that the sample came from, and what's required to determine cause and effect. So let's take a look at an observational study versus an experiment. So an observational study observes individuals and measures variables of interest. So it's not trying to influence their responses. So there's no treatment imposed. An experiment can impose a treatment, meaning it's requiring people to randomly take a placebo or randomly take the drug of interest. So if a pharmaceutical company conducted a study, they would be just collecting information. Maybe what percentage of people with high cholesterol take our drug or take the various drugs available. Now, if we did an experiment, what they might do is maybe they have one other drug competing with them to lower cholesterol, and they might assign 3 different groups. So they might take in a random sample of the population that they're drawing from. So they might have all the people in San Francisco that have a high cholesterol. Now randomly choose 90 with an SRS. Then they decide to break up those 3 groups, randomly assigning them to their drug, the current drug on the market, and then a 3rd group where it is a placebo, like a sugar pill. Now, what's required to determine cause and effect to see if their drug is more effective is that random assignment. So in order to apply our results to the population, so if we're in San Francisco that we took our SRS from, then we could determine that we could apply our results to people with high cholesterol in San Francisco if we took an SRS from that group. We can do that because if it's random, it's more likely to be representative of the population. If it's not random, there's likely to be some bias in there. Like maybe it's only people who were motivated enough to go out of their way to sign up for the study. And perhaps those people are also more motivated to do the other things besides take a drug that lower cholesterol, like change their diet and run. So we need a simple random sample in order to apply our results to the population that the sample came from. Once we have our simple random sample, we need random assignment, randomly assigning to groups in order to determine cause and effect. In this case, does the drug of interest actually lower cholesterol? So in this example that I'm giving you, there's randomly assigning to 2 groups. You could do random assignment to multiple groups. And then ideally you would have a double-blind experiment. A double-blind experiment would be one in which neither the person receiving the treatment knows if they're getting the current drug, the former drug, or the placebo, nor the person administering it. So whoever's giving them the drug doesn't know which one they're getting, whoever's getting it. So that way you get rid of this placebo effect that exists. So an experiment's the only way to have fully convincing data that a treatment's effective. If we just gather data in a study, we can't determine cause and effect. So the main difference is a random assignment to treatment groups in an experiment. So here's an example. Pause right now and read over the example about an observational study versus an experiment. Now this is an interesting example because when we just make observations without actually conducting an experiment, then it might seem like one thing is causing another, when perhaps they're only correlated. And remember, correlation is not causation. So several studies were showing that from medical organizations were showing that taking hormones reduced the risk of heart attack in women by 35 to 50%. So one thing that's good about that is that prompts an experiment in order to determine if the hormone treatment's really causing this decrease in risk. So to test this, they were randomly assigned to one of 2 groups by coin flip. That's one way to do random assignment. If you have 2 groups, you have heads and tails. Heads, you go to the treatment group. Tails, you go to the placebo group. So they looked at age and hospital visits by year. Those are lurking variables that would require blocking. So blocking is when it's like if we have another lurking variable that we think might affect the outcome of our experiment, for example, your age or how often you go to the hospital, we might separate those into different groups. Like women in their 60s have one experiment that we look at separately. They're separated into a block, and we only compare them to other women in their 60s. So before we randomly assign them to groups, we'd separate them out by age groups. Women in their 60s, then randomly assigned to treatment, placebo, and just compare within that group. Then do the same thing for women in their 50s. We could also do the same thing with hospital visits per year. There are likely other lurking variables too. So what we found in this experiment, or what they found, was that the lurking variables were income and level of education. So women who chose to take hormones tended to have more money and have a higher level of education, so they saw doctors more often. So here the lurking variable that actually caused that decrease in risk was their income and their level of education, and how often they went to the hospital. So it seemed that that was what was going on, but when we conduct an experiment we can find out that it's not, that the hormone treatment was not the cause of the lowered risk of heart attack. So again, a study indicated that might be true. Turns out there are other lurking variables, and that's not the actual cause. And we can only determine that with an experiment. So keep in mind that a lurking variable is some variable that the study hasn't accounted for that's affecting the response variable. And when we have a lurking variable, it confounds our results. We can't tell the effects of the explanatory variable and the response variable. There's another explanatory variable that's causing some change in the response. So we'd have to control for that. And if we find that that's going on in our experiment, they would likely redesign the experiment and do it again. So well-designed experiments are key to getting data that actually tells us cause and effect and allows us to apply our results to the population. So I mentioned that a treatment is the main difference between a study and experiment. A treatment is just when you impose some type of condition on the experimental units, or if they're humans, experimental subjects. So when we impose a condition, it's called a treatment. That's what makes an experiment. We can determine cause and effect if we also impose that treatment using random assignment to different groups so we can compare. So we would ideally want to just test one explanatory variable at a time. If we feel like there's another, we might use blocking, where we separate out based on, like if we felt before, as mentioned, age was affecting things. We just compared women of the same ages as we did our experiment. And then you could go on to look at other possible explanatory variables, control for the one you're currently doing, and test to see if they're actually causing something too. Key thing though, if we really want to know if our explanatory variable is causing a change in our response, is to have random assignment. Or you're creating groups by chance to make them more comparable. If we can create them by chance, then it's likely there are less lurking variables. We didn't happen to put everybody who is in their 50s in one group and everybody who's in their 20s in another group. So that allows us, random assignment allows us to determine cause and effect. It can be carried out by flipping a coin, drawing names out of a hat, with Table D as we did in class, or with another type of technology. It allows us to make inferences about the population. If we took an SRS from a population, we can apply our results about cause and effect to the population from which we drew our sample. However, if we did not take a simple random sample, let's say we had volunteers sign up for an experiment, then we can only apply our results to the group that was in the experiment. So if I have volunteers sign up for an experiment and then do random assignment, I can determine cause and effect, but I can only do it for that group. There's likely another lurking variable there, so I can't apply it to the whole population. So an SRS from the population if we want to apply our results to that population, random assignment if we want to determine cause and effect within an experiment. Good principles of experimental design are control for lurking variables that might affect the response. Compare at least two groups in a systematic way with random assignment so that you lessen the likelihood of lurking variables. Randomly assign within there to using chance to assign groups to even out characteristics and make those two groups mirror the actual population better. And then replication. Use enough people in the experiment and repeat the experiment. So replication within the experiment, meaning having enough people to really figure something out. If you just have 5 people in an experiment, it's tougher to see what's going on because we don't have a large set of results. And then repeat the experiment so we get to see if we can verify our results. You want to make sure within an experiment you treat the subjects or the experimental units identically. So this is why having a placebo pill is good. If one group's not taking anything, then there might be a mental effect where they just don't think they're going to get better, and that has a large effect or a large possibility of having an effect on their condition. So a placebo effect is something we're going to look at in class. It's also good to not have the people who are administering the treatment not know, and so whether they're getting the treatment or not. So that's called double blind, when both of those groups don't know. Now, if an observed effect is so large, so if we see that the group, like this effect of this drug, for 95% of the people, it lowered their cholesterol 20%, then we can say that it's statistically significant. And this is going to be a key that we're going to explore in second semester a lot. Quantifying what statistical significance is. What does it mean to actually truly prove that something is significant? Right now we just know that if it's such a large effect that it would rarely occur by chance, we call that statistically significant. As I mentioned at the beginning, blocking is one way to account for some lurking variables. So blocking would occur before random assignment. So if we felt like something like age affected the possible outcome of our experiment, we could create blocks. Block is a group of experimental subjects or units that are similar in some way that might affect the outcome. So we put, like I mentioned before, putting all the women in the experiment that are in their 20s in one group and then randomly assigning to a treatment or placebo. Then do the same for 30s and only comparing women of the same age groups to each other in order to account for that. So pause right now and read this about laundry detergent. So in this case it would be experimental units and how we use blocking based on the color of the clothing. When we describe how to blocking, here's what we draw a little design here. We have our many pieces of dirty laundry. Since we think whether it's light colored clothing or dark colored clothing could have an outcome on how effective the cold or hot water is, we separate them into blocks, meaning we only have light colored clothing here, only dark colored clothing here. Then we randomly assign to cold or hot water using a coin flip or one of those other ways we've talked about. Then compare cleanliness of the two just within light colored clothing, and then compare dark colored clothing that was in the cold water to the hot water. So here's a nice visual on what we mean by blocking. Another nice way to do it is to have a matched pairs design. It's a type of blocking. It's a type of blocking in which we control for lurking variables by we match pairs of similar experimental units. So maybe we investigate twins would be the ultimate matched pairs, or comparing you to yourself to account for other lurking variables. So we're going to look at this example in class of a matched pairs, but it's where you match up pairs of similar individuals and then have one get the placebo, one get the treatment, and compare just within each pair. That's a specific type of blocking and different in that sense. Here's your multiple choice question. Before answering it, you should go through and read the summary in the book and look over the lesson and the examples. One key thing I want you to focus on is the difference between stratified random sampling, which is during sampling, and block design, which happens during an experiment before random assignment. That's one thing that's a common mistake for AP Stats students. So here's your multiple choice question. Please pause the video and read it over. You're looking at this situation and deciding if it's a study or an experiment, and if so, which type. Remember to also look over the vocabulary posted on Schoology.